So happy New Year to everyone, and thank you, Henry, for coming here with the first seminar of the year. And we have Henry Sinclair-Banks from University of Warwick talking about coverability in VASS revisited, improving Rackoff's bound to obtain conditional optimality.
Thank you very much, everybody. Yes, hi. Nice to meet you. I'm Henry. I'm a PhD student from the University of Warwick, and today's presentation is going to be about the most interesting parts of work that I did with my Université and Coverability for ICAP 2023. Yeah, so I think the best thing is just to get started with an example to get familiar. So a vector addition system of states consists of some directed graph, here's an example, and integer weights labeling the edges, here's an example. And the coverability problem asks, from some initial place or initial state A, can I reach some target state, in this case G, via a path that's never negative? Very nice. So in this, when I say never negative, what I mean is I'll start with counter values on the first and second components. They'll start with 0, 0. And when I take a transition, I'll add component-wise to the vectors. So notice from A, I could either go to C or I could go to B, but I can't actually validly go from A to C directly because I'd subtract 7 and I'd enter a negative. I get a negative value on the first component, and that's not allowed. So for a valid configuration, I would have to go over to B. And when I go to B, I'll have values 2 and 0. And from B, I can either go to C or over to D. But again, if I were to go to D, I would end up with -4, and this is not allowed. So I have to go up to C, and now I have 5 and 8. Okay, but now I'm forced to go to E, and at E, I'll have 3 and 10. And then from E, I can get to D with 7, 5. And notice that I'd like to get to G. I don't care about the values. I just have to have non-negativity so that the first and second components just have to be at least 0. But notice I can't get there yet, right? If I go via F, then I'll have -8 over the first component, I'd go negative. And similarly, if I went directly, then a -20 from 5 would get me to -15. That's also not okay. So I'm almost stuck. So you have to think really hard. It's a bit early and a bit too fresh in the year and a bit too cold outside to work this one out. But I found a cycle earlier. Here's one I made at home. You get 1 on the first component, right? Because you get +5, +2, and then -6, and you get 10 on the second component. And so actually, I can just take the cycle as many times as I like, right? I can pump both components to arbitrary values. Turns out that just doing this twice is fine. I get to values 9 and 25. And from here, actually, I can take either via F or directly to G. And I'm happy. This is a positive instance of the coverability problem in vector addition systems with states. And this two-dimensional just refers to the number of components. So I can make this much more difficult and give you a bigger headache and ask for 3 components or 4 components or 5, but I'll save you the hassle. I hope that makes some sense. We're going to be talking about these systems in great detail today. But first, why am I even here? Why am I talking about them? I can think of maybe 4 things that you might be interested in. Maybe there are others. So the first is you can describe discrete resource management problems as exactly these systems. It's a bit of a silly example where you might have a hybrid car, right? It has a battery and a fuel cell, and maybe there are roads around a network that look a lot like a directed graph, and now you can write down the costs of the roads as how much fuel and how much battery they cost, or maybe you gain battery back by regenerative braking, maybe it's a downhill road or something, right? And then the coverability problem just asks, can I get to work from my home, right? It's a very natural problem. You can also see VASS as Petri nets, they're an equivalent model of computation. I won't explain why and how, it's not particularly difficult, and probably all of you know it. And Petri nets can model all sorts of things. In particular, they're a model of concurrency, as I've titled. You can also see this as a model of, or a discrete model of a chemical reaction, right? You can have the input places being the fuel for a reaction and the output places being the product. And the transition just says oh, this is the reaction that is occurring. And so you can reaction that reacts this way. You can also test safety. This is maybe a bit of application focused. Imagine you have some concurrent system. Maybe you have a very simple model of a computer with memory, storage, and a processor. And you maybe have the oldest processor on Earth that can only have 1 thread running at any given moment, right? So that's 1 total, 1 value on that place. A set of bad configurations might be, I have at least 2 tokens on the processor, right? Because you don't want to write over the original program. And so now you can write down a set of unsafe configurations as a coverability objective. And so then if you want to test coverability, can I get to a configuration in which I've tried to write down 2 programs to my single thread processor? And this is somehow positive coverability is a witness of unsafety. And you might be more interested in related problems. Unboundedness is very similar to coverability. Instead of from an initial can I cover a target, it asks, can I see an unbounded number of configurations? What this will end up looking like is some path to a configuration and then a cycle back to the same state that has a non-negative effect on all the components, and then you can make this mask a number of times. So it's kind of like coverability with a bit extra. There's the reachability problem. This is fussier. Instead of just getting to some specific state, I'd like to get to that specific state with exact values of components. Much harder, and then maybe more historically important. It turns out that coverability is exactly equal to some commutative semi-group uniform word problems that have appeared in the literature. But I guess these things are still studied. I won't be talking about them, but some of the motivation, it does indeed come from these problems. Okay, so what I'm going to show you, the first I'm going to give you like what was known before. Not everything, we'll be here forever. So I'll give you the like important landmarks as to what was known before. And then I will show an improvement. The perhaps most important result that we have is to Rackoff's. There will be two interesting parts here. Well, maybe more than two. I'm not promising more than two though. I will introduce the notion of thin configurations, which we hope are very useful elsewhere. And we're going to show them how we use Rackoff's bounding technique. Like our approach is actually quite similar, but we're a lot more careful. And then from this, we get two algorithms for coverability. One that is optimal unconditionally in space, and the other that is conditionally optimal with respect to time. I'll explain why. And then hopefully I'll get onto showing the conditional lower bound because we bring that as well. For this, we'll be showing how to detect cliques in graphs as instances of coverability from some funky reduction. And we do this via simulating bounded counter machines. Okay, so without further ado, a little bit on the history. I'm going to keep these two letters for the whole presentation, so don't forget. D is the dimension, nice, and N is the size. We encode everything in unary. It turns out not to be important, but I won't focus on this today. Like it's not so critical for the presentation. To be really clear, this is the number of states plus the absolute value of every update that you have in your system, right? Just writing it all down in unary. And so with these two, we can start to study the complexity. The first from 1978, from 1976 is the lower bound from Lipton, which says that coverability is exponential space-hard. And then 2 years later, Rackoff goes like, oh, actually, coverability is in exponential space. And so you might be already falling asleep, going, oh, we're done, this problem's exponential space complete. Like, what's the point? Well, the point is, let's look a little bit closer. Actually, Lipton said specifically that coverability in VASS requires something like 2 to the d times log of the size of the system space to be really exact. And the way he went about this was by constructing particularly nasty instances, as one might expect. They require doubly exponentially long runs, like n to the 2 to the constant times d. They are aptly known as Lipton's construction. How on earth does he do this? That's a whole presentation, but I'll give you just a flavor of a nasty-ish instance. The simple system, and I would like to show this as exponentially long runs of witness coverability. So suppose you're looking to witness coverability starting at P with 0 on all 5 components, and you'd like to get to Q with at least 0 on all 5 components. Well, notice that final step to get to Q, you have to have 1 on the final component, right? And to have 1 on the final component, you have to take that final cycle once. And to take that final cycle once, you need at least 2 on the penultimate component, right? And to have at least 2 on the penultimate component, you have to take the previous cycle at least twice. And to take that twice, you need at least 4 on the middle component, and that requires this cycle to be taken 4 times, etc., etc. And so when you sum it all up, you realize that, well, actually, this requires exponential in the dimension, right, which is 5 in this case, number of transitions in total in your whole run, like for the length of the whole run, to witness coverability. Now, this is a bit of a far cry away from Lipton, right? I just gave you 2 to the omega d, roughly. Lipton does a lot more. I won't show this, but just to kind of convince you that such examples might exist. And then Rackoff gave something complementary. He says that coverability can be decided in exponential space, but precisely 2 to the constant times d log d times log of the size of the system space. There's a little gap here, and that's what we're going to focus on. And he did this by arguing the kind of opposite, in a sense, of what Lipton does, known obviously as Rackoff bound. He argues that there are runs of this exact n to the 2 to the constant times d log d length runs, no matter the instance of coverability that you ask for. I will show you how this works today. And there was a question asked a few years later by these two chaps, you may know, Mayor and Mayor, it wasn't really a question. It was like a demand, like improve these bounds, right? They really wanted to see that log D factor shaved or the lower bound improved. And I think that I really have to give credit to Rosier and Yen as well on this slide, because the exact phrasing of the problem changed over these years slightly, whether you had states or whether you didn't have states. And Rosier and Yen actually ever so slightly improved Rackoff's upper bound. So really, these theorem statements are actually thanks to both Lipton, Rackoff, and Rosier and Yen. Okay, and we'll be using the technique of Rosier and Yen later, so keep that back in mind. Right. I will now quickly remove states to make my life easier and to make your life easier. But I won't explain exactly how. I'll just give you the definition, and hopefully maybe you've seen this before. So a VASS with states has, well, states and the transitions move you from one state to another by updating the counters. And well, a VASS is just, you can imagine it as a single state where all the transitions are self-loops back to that state. It turns out that obviously a configuration is a pair of a state and the current counter values versus just the current counter values. And a lemma from Hopcroft and Pancio in 79, you can simulate the states with 3 extra dimensions. And because we're going to be dealing with VASS for which the dimension is not fixed, we're going to just remove states at the cost of a constant number of dimensions, no problems with the complexity. I won't explain how this works, but it kind of works in a way via you represent the current state on one of these 3 counters, you represent some information about the system on another, and when you want to move between one and the other, you kind of juggle the information between them. Like if you were to try and swap 2 program variables in your program, you have like a third auxiliary to help you swap around. It works kind of like this, but it's a little bit more involved because you only have integers at your disposal. So yeah, the takeaway, the message, the reason I've had this slide is we will just work on VASS because we do not fix the dimension. That's all you need to know. And so now we can talk about Rackoff's upper bound because he talked about it without states. So our contribution, the improvement that we have, is that coverability in VASS is always witnessed by doubly exponentially long runs. But in particular, we do not have this double exponential log D factor. We have just n to the 2 to the constant times D. Fantastic. And well, to spoil the fun, it's basically Rackoff's proof, but we're a lot more careful. We introduce a new definition, and we're much more precise with our sharp countervalue bounds. So this is what Rackoff did. He defined an extremely large value, made a box in D dimensions, and said, if a configuration ever was to leave, so in this case, counter 1 exceeds a certain value, it's so large that for the remainder of the run, even if it decreases maximally from that moment onwards, it will remain above the target, but you can kind of forget about it. And so then you can recurse into solving coverability on a system with 1 less dimension, and you continue this way. We do the same thing, but we're much more sneaky with our bounds. Our bounds are no longer like uniform. We don't have a massive hypercube. We have this L shape of sorts. We argue the same thing. If you ever see a configuration with sufficiently large counter values as defined by our shape, you recurse, you remove that component. In this case, counter 1 and counter 2 actually both have values greater than necessary. So this would actually, in the 2-dimensional case, recurse down to a 0-dimensional case, but never mind. So what does it look like in 3 dimensions? So we actually have a sequence of bounds. The largest is bounded by a certain value, the second largest is bounded by a smaller value, and the third largest is bounded by another value. We permute over all bounds. So in this case, over all orientations of the 3 components. So in this case, you get 6 possible places that your configurations can be quote unquote small. We actually care about the union of this thing, and someone 3D printed me the union of this thing, which is really cute. I was really appreciative when I saw it on my desk the next morning. But this is kind of, I show you this not just because it's fun, but also because it really shows you the improvement, right? Rackoff's is the box that contains this shape. And our shape is, in this case, in 3 dimensions, something like half the size or even smaller. This isn't really true to scale because the components get exponentially longer. In this case, they're like side length 3, 2, and 1, so it's not really doing it justice, but I hope it kind of demonstrates that if you imagine the box that this contains, like we really save a lot of space. That double exponential log D factor is somehow really significant because it's double exponentiated. Okay. What exactly is a thing configuration? Like, how do we define these things? So imagine you sort the components, and then we have some specifically chosen values for each. So M1 for the first component, M2 for the second, etc. As long as your values are less than M1, M2, etc. after sorting, then we'll reconsider the thing. So in this case, the first component of V is less than M1, and the second component of V is less than M2. So V is a thin configuration. And to get an improvement, we will have M1 significantly smaller than M2, significantly smaller than M3, etc. I'll define them in just a moment. So they actually grow doubly exponentially. So M1 is something like n to the fourth 0, and the next one will be n to the fourth 1, n to the fourth 2. This 4 isn't magic. You can replace it with a 3. Hopefully we can replace it with a 2, maybe a 2 plus epsilon. Don't worry about where the 4 came from. It will fall out of the proof. It'll be clear why we're very lazy with that choice. But as long as it's constant, we get an improvement. And so one might ask, like, how many thin configurations are there, right? Like, that's what we want. After all, we want to improve the balance. So how many thin configurations are? Well, I told you that each box, right, will have M1 by M2 by M3 many configurations inside of it. And there are going to be like d factorial many ways of jamming this upper box into the corner of your axis. And so you get d factorial times M1 times M2 times M3, etc. I will just show the maths. It will look really ugly. It's just to kind of give you this in the back of your mind. It will pop up in a couple of slides and we'll work with it. We'll massage it out. So I've substituted in the values of M. And then really this is just d factorial times n to the d, because this n occurs d many times this product of the sums of 4 to the i's. Again, this is ugly, but it will become clear why I break it down soon. So how do we actually bound the length of coverability runs? So this is the overall proof structure of Rackoff's, just from a high level perspective. So the first thing is, imagine you'd like to do coverability from some vector u to at least some vector v. So a positive instance here would be to be able to reach some point that is above and to the right of v. So imagine there's a run. In fact, imagine that you have the shortest possible run in terms of the number of transitions that you take. From u to some vector w, and notice that w is indeed to the right and above v. So we're going to split it about the first non-thin configuration. So this x value is where it escapes the box. And we're going to like stare at these two parts separately. The first part we'll call the thin part, naturally. And its length is just going to be bounded by the number of thin configurations. The reason for this is because, well, imagine you have a thin run whose length is greater than the number of thin configurations. So this thin run has to sit within inside the box. If it sees more than the number of thin configurations, it must, by pigeonhole, have seen the same thin configuration twice. And if it sees the same thin configuration twice, then you just have a cycle where your overall effect is 0, right? You can just cut this out of your run, and you have a shorter run, which would contradict the fact that you started with the shortest run. So indeed, your thin configurations can only wiggle around the box once before leaving. And so this is a bound on rho, the thin part of the run. And yeah, indeed, it's going to be less than or equal to that nasty thing that we computed on the previous slide, the number of thin configurations. And then the second part is, we'll call the tail, is when you leave. You know that from x, in this exact case, the second component exceeded some large value. Very informally, it was so large that for the remainder of the run that we can forget about its value, we know will stay not only non-negative, but above the target. And so we will ignore it. And I will prove the claim that the tail of the run has its length bounded above by this double exponential value, n to the 4 to the d minus 1. And so in total, the length of this run, the length of pi, will be the length of the thin part, the length of the tail added together. This will be this nasty thing plus n to the 4 to the d minus 1. But notice we already have an n to the 4 to the d minus 1 floating in here already. So really this term will dominate, absolutely. And so we'll need to show that this, in fact, is the improvement that we like. But I'll prove claim 2 first. So claim 2 is really like Rackoff's inductive argument. It's really pretty. Yes.
Always V and W must be thin. Thin is defined in a way that the source and destination of.
So W need not be thin. W could be some very large value, but actually U and V, this is kind of comical. Look at the definition of M1. M1 is n squared. That these values at U and V, your source and target, will have values less than n. And so actually you can kind of put them inside a box within M1. Your source and target are particularly small. W might not be that. That's slightly separate.
Then if you go on the next slide, the length of tau is less than n for d minus 1. It still requires something about value. Does it?
No, it doesn't require any information about W.
Just about X.
Yes, just the components that X exceeds. I think it will become clear. I hope so. But ask again if it doesn't. So, okay, let's prove this. So we're first going to, just very informally, we're going to sort the components. So we'll have the first component is smaller than the second, is smaller than the third, etc. I've done this diagram to match that on purpose. So notice the first component value is something around here, and the second component value is much, much larger. So if we know that X, the first non-thin configuration, by the definition of thin, well, we must exceed one of the bounds on one of the components. So in this case, I will be 2 because we know that X2 exceeds M2, right? That's the whole point. And actually, because we've sorted the components, we know that this will be true in general. So we know that although X2 is at least M2, X3, X4, X5, etc., all the way up to XD will all be at least that bound as well. So they'll all be, quote unquote, sufficiently large. And in particular, MI was n times n to the 4 to the I minus 1. As I was explaining in this example, X1 is less than M, so we don't violate thinness on the first component, but we do violate thinness on the second component. And so we'll focus on splitting about the first I minus 1 components that kind of remain thin, and the remaining I through D components that are somehow sufficiently large to be ignored. So let's focus on the first I minus 1, and then we'll check with the remaining components later. Let's see what happens. So by the induction hypothesis, I claimed that there'll be a run where if you just completely ignore the remaining I through D components, there'll be a run that witnesses coverability of length less than n to the 4 to the I minus 1. So this will be some alternative path I've denoted red tau prime. It will start at x1 through xi just on the first I components, and it will reach some configuration. Might not be the same one, be some y, for which y1 through yi minus 1 are at least the target b, right? Notice that y, this picture is a little bit suspect. You can imagine this picture is just for the first I minus 1 components. And indeed, it's at least b. And we know this is how do we check that we're okay on the remaining components? Well, the length of this red path tau prime is less than n to the 4 to the I minus 1. What's the worst that could happen to the remaining components? Well, suppose you subtract the greatest possible value at every single step during tau prime. So you start at x and you follow tau prime, look at the remaining components. Maybe the greatest effect is minus n, right? The size of the system. You can't get a greater negative effect than the size of the system. And so potentially on components I plus 1 through D, you subtract n every time. And this is a subtle part of the definition. The length of a path is the number of transitions you take. The length of a path is the number of configurations. So the number of transitions that you take is one less than that, right? And so the maximum negative effect over the whole run is minus n times the number of times you take a transition, which is the length of the run minus 1. So that's the worst that can happen on the remaining components. And so then let's stare at the values. Well, I know that these components had values xi through xd, and these were all at least that mi value that was chosen earlier. That's n times n to the 4 I minus 1. And so then if you then from x1 to xd take tau prime, the new path, well, you're going to subtract at most that value from each. And you know that you'll be left with at least n on every component, because the length of tau prime is n to the 4 to the I minus 1. So at the very end, you're left with something at least n. Not much, but the point is that you'll stay above n. You remain non-negative, which is nice. And actually, you stay just outside of this box. So you know for a fact that y will be outside of this box. But answering exactly your question earlier, we know that the target configuration will be inside this box. Your target configuration cannot be bigger than the size of the system, which is n. And so then you know that y is outside this box, and so clearly you're fine, right? So n is at least vi through vd. So looking back, induction told us that the first I components were at least the target. That was for free. And then if you follow the worst possible case for the remaining I through d components, we know that you'll be at least vi through vd, and so we cover the target, and so we're fine.
So we discussed I to D. How did we conclude about 1 up to I?
We just invoke the inductive hypothesis. So so we're sort of supposing that for components 1 through d minus 1, that there is a run of length n to the 4 to the I minus 1 for which you witness coverability. And so we just get this for free. So I've technically not written this full claim out. It's really there exists a run of length at most 4 to the n, at n to the 4 to the I minus 1 that witnesses coverability. So if you add that to the claim, does that help? Fantastic. And so the highlighted boxes just say that, well, this is indeed, if you just set I equals D, we're done. Like, that's it. It's all we wanted. Does this make sense? This is the proof. This proof works if you replace our notion of thin configurations with just MD everywhere. You just have the box. That's Rackoff's proof. There's literally no difference, other than the fact that Rackoff's choice of MD is not exactly the same as ours. We choose n to the 4 to the d minus 1. Rackoff chooses, I think, n to the 2 to the d minus 1. But up to that constant, the proof is exactly the same. But you don't need to do any of this sorting. You don't have to be so careful with his.
So he was able to have a smaller bound because the fact that he was considering the whole Q.
His bound is greater because his bound here was ever so slightly smaller. But think back to the first part, right? So for claim 1, instead of running through all the thin configurations, Rackoff could, in theory, run through the whole massive box. That box is really large.
That's the length of tau prime that could be much larger.
So in his proof, length of tau prime will be comparable.
Yes.
But the length of rows, the bit that I've used in the past, might be absolutely massive. So actually, our tail will be similar, if not slightly larger, but our thin part is really where we save. That's very apparent with the proof. So how do we prove the main theorem? Well, again, let pi be the shortest run witnessing coverability, and I'll split like I did. We have claim 1 and claim 2 that allow us to write down the length. We can bound this now. And so this kind of answers your question. This term absolutely dominates. It dominates it so much, I'll be lazy. I'll just say that, well, actually, we'll bound the second term above by the first term. Okay, how do I work with this now? Well, it'll work if you really care. If n is at least 2, which is very reasonable, like having a system of size 1 is crazy. You can have a database for your systems of size 1 if you really want. So we'll have all systems of size at least 2. We have this bound that d factorial times n to the d times 2 is bounded above by n to the 2 to the d. So substituting that in, we get n to the 2 to the d times that nasty sum. Well, really, this is very easy. Notice that if you sum the powers of 4, right, from 4 to the 0 plus 4 to 1, all the way up to 4 to the d minus 1, and then you add 2 to the d, well, that 2 to the d that you added in there basically makes no difference. This is definitely less than equal to 4 to the d. This inequality holds for if you replace 4 with anything like 2 plus epsilon. This will hold. And so we can substitute that in and we're done, right? Because n to the 4 to the d is just n to the 2 to the 2d, and that's just a constant times d. So this is now a bound of n to the 2 times OD. I gave a very similar version of this presentation a little while ago, and I got instantly asked, where's 4 coming from? Like, why is 4 special? It's really just to make this math simple and we get a constant. It would be very nice to have a sharp bound. And we believe we have this with workload at the moment. To get a sharp bound without any O, we think we get something like n to the power of 2 to the d plus d, like something really small, where this plus d is in the first exponent, not the second. I hope that makes sense. Cool. So that's the main result, right? Like that's the important bit. So what follows? Well, first we can derive 2 different algorithms for coverability. They're really the same algorithm, but you view their complexity in a slightly different perspective. So the first is that you can decide coverability in exponential space. So how do I do this? Well, if I have runs of this length, imagine now the maximum size of a configuration you can is. If you just have a run of length n to the 2 to the d, then the largest configuration that you can see can be written down using log of that many bits of memory. And so you can then explore the space of configurations non-deterministically and just happen to guess your path directly there. And if you can write down a configuration in log of n to the 2 to the d many bits, then clearly the algorithm only requires, space. And this is optimal because if you remember from the earlier slide, Lipton gave a lower bound that said that coverability requires 2 to the omega d times log n space. So up to the constant factor in our exponent, we're optimal with Lipton, and that's unconditional, which is fantastic. Well, where does conditional come from? It comes from the second. Instead of non-deterministically searching the space of configuration, deterministically search the space of configurations. And you can do this via breadth first or depth first search, however you like. And it turns out that this will be conditional. And I will explain why now. So we're going to condition on the exponential time hypothesis, and we're going to get a lower bound of the form n to the 2 to the omega d. So it's conditional again up to that constant in the second exponent. What is exponential time hypothesis? How do we use it? So the variance is very wavy. The more precise statements can be found in the literature. Basically, 3 sat with k variables takes 2 to the omega k time. That's the variation of exponential time hypothesis I'm going to use. We only care for the following corollary, and I like to put faces on slides for people, like I like faces on my slides, but this is thanks to too many people, so I couldn't put all of their faces down. The problem we will care about in particular is whether you can detect a k-clique in an n-vertex graph. The exponential time hypothesis says that this requires n to the omega k time, and thanks to these wonderful people, you can actually assume your graph is k-partite. So finding a k-clique in a k-partite graph really asks, can I pick a node from each of the k-parts, which makes a k-clique? And so that's the problem that we're going to reduce from. But to get the double exponential, we're going to use an exponential value for k. Right, that's why I've used k here. So we're going to use k equals 2 to the d. We're going to look for a clique of size 2 to the d. And if indeed, in an n-vertex graph, if indeed we can do the reduction, then you just replace n to the omega 2 to the d inside. Actually, I've given a slightly relaxed statement at the top. Our lower bound will be that coverability requires n to the omega of 2 to the d time. I just shifted that omega up just to make it look slightly pretty. It's actually ever so slightly weaker statement than what we get, but it's very subtle. Okay, so how do? We're going to reduce to coverability, but we're going to go via bounded 2-counter machines. So first is we're going to reduce coverability. First, we're going to reduce to coverability in doubly exponentially bounded 2-counter machines. You might be asking what they are. And then afterwards, once you know what they are, once you're happy with that first step, we're just going to simulate doubly exponentially bounded 2-counter machines using polynomial size, d-dimensional normal VASS. So what on earth is a doubly exponentially bounded counter machine? So it has 2 counters. I'm going to call them x and y, and they're going to be called x and y for the remainder of the presentation. They can take values between 0 and that exponential value that I've specified. And the operations that you're allowed in your bounded 2-counter machines, you're allowed to add and subtract, and you can test for 0. This is scary dangerous because, well, 2-counter machines have unstable readability. So, I mean, this is really terrifying. But because they're bounded, they have a seriously large but finite space configuration. So it's okay. It's okay. What does this program do? Here's an example. Imagine, that was the wrong way around. Imagine you start with some value x. Let's say x is, 10, and y is 0. You take the first loop, you'll move your 10 from x to the second onto y. You'll then make sure that you did that fully. So now y has 10 and x has 0. And then you add it back, going from y back to x. But this time you'll subtract 1 from y and add 5 to x. And then you'll force that to happen fully, because you'll set y to be 0. And so this program does multiplication. These things are quite powerful. And so if you started with the precondition, like some value on x, 0 on the first, you'll end up with a postcondition 5 times that original value and 0. And then, yeah, just to kind of make it clear, why I'm writing these things down as counter programs. This is just for sake of presentation. Here is the VASS, the bounded 2-counter machine rather, with the 0 test that corresponds to this thing. So these drawings get large and ugly as these programs get large and ugly, but you can write these down slightly more succinctly. So I'm going to write them down like that. Hope that's okay. That's reasonable. Yes. Does this make sense so far? Definition's okay, because we're going to talk about bounded 2-counter machines. Right. I will also give a name to this guy because we're going to use an order. Okay. We're going to call it a multiply. Multiply also has the sister divide. the same idea. Instead of subtracting 1 from the first component, you'll just subtract, I don't know, 8 at a time. And so you can only pass through this if indeed the original value of x was divisible by 8. And the result will be that you have an eighth of the value when you go out. Again, we're going to use the system divide many times. Okay.
Sorry, may I ask?
Yeah.
I don't know, maybe you explained it already, but how do you encode the conditional VASS? Because the VASS might have many runs. One of them will be the one that's equal to 0, or
so
can you encode it?
No, this is like we're going to force a run is valid. So yes, the question is like, what is a valid configuration that allows you to take this transition? If x has value greater than 0, you are not allowed to take this transition. So it's just an invalid.
But it's just a condition on the VASS. It's not that you can encode it in a normal VASS.
We will simulate these machines later. Without that bound, no. With the bound, yes, you can. Okay, you can do this following really silly encoding into a VASS without counters, like a big directed graph. Just take a massive space of configurations and have an edge between 2 nodes in this graph if you can traverse it in the original system. They'll be absolutely massive. We will be more efficient than that. So the short answer is yes, but not directly.
I lost track. So you are defining the bounded to continuation. Is it for an upper bound or a lower bound?
For a lower bound, because we have a lower bound on the time required for detecting a clique in a graph. So we're going to use that. We're going to take that problem, which has an exponential time conditional lower bound. We're then going to generate an instance of coverability in this system.
Yeah.
We're then going to generate an instance of coverability in a VASS from that.
Yeah, so then this bounded to confirmation. Here, the lower bound is what something known about it?
That's a good question. So I don't know off the top of my head. I know that if you're asking for reachability in a exponentially bounded, not that exponentially bounded, but it's an exponentially bounded one count machine, reachability is p-space complete. This thing's going to be really hard, but I don't know.
These bound, I mean, those
Yeah.
machines. Wait. If you have just 2 counters, you lose 1 exponent in this encoding. So if you have 3 counters,
Yeah.
then you remove 1 exponent from the bound and you get that bound for the results.
Yeah, so because if here the
Space bounded Turing machine.
because there is a XP time hardness for bounded counter machine, but if the bound was given like in the binary. Okay, so then if you use what you're saying on top of what is already in the then would it give an XP? I'm a bit confused. Sorry. Okay, please go ahead with this.
Yeah,
because somehow this machine has been already defined in the literature.
Oh yeah, there's nothing original about this machine. And actually the simulation result that goes from this machine to VASS is also very old. And so I have a feeling that this will be done.
Okay, we talk more.
Okay.
There was an open problem on the probabilistic setting, and to show XP time hardness, it was open for a long time. A problem was XP time or EXPSPACE-hard, and then there was a reduction through this kind of boundedness counter machine, not even 2 counters, it could be bigger number of counters. But the bound here required a little bit smaller. So the bound was like binary. So you knew that you would not, like when here you say bounded in that time, it's a bound on the counter.
Yes.
So there they had a bound on the number of transition, which will imply a bound on the counter.
Yes.
And then they prove XP time hardness.
Okay.
Which solve the open problem of hypothesis for a long time. I will show it to you. Yes.
Okay. So how do we implement detecting a clique in these machines? So here's a clique I made earlier. So it's going to be k-partite, and it's going to have n vertices. I'm going to associate a prime to each vertex. So I've written down, I believe these are primes. If they're not primes, I'm sorry. And we can now represent a candidate selection of nodes uniquely as a product of k primes. And so I can write down just one number and say, like, this, I promise, is going to be a clique. And so that's what we're going to do. So I'm going to guess that my clique is something like 2 times 7 times 13 times 23. And how do we do? So remember, we have multiply and divide at our disposal. So how do we write this down? We're going to write this down as a conjunction of multiply and divide statements. So what we're going to do is we're going to check whether the guess is divisible by some edge between V1 and V2. To check divisibility, we just take the value, divide it through, and then remultiply it back. If you can complete this step, then clearly you are divisible by the original value. And so when I write down like a divisibility check in your mind, just add that we're doing a division and then a multiplication step. And so for every pair of vertex subsets, Vi, Vj, we'd like to be able to have picked an edge for which its endpoints divide the guess. And if that's true for every pair, that means that for every pair of vertex subsets, we are able to pick an edge for which we have picked its 2 endpoints. Therefore, we have picked a clique. That's what this means. So we can go through and check for every pair in this case. Actually, there are more subsets that I haven't written down, but this is good enough for this example. And so the formal statement is there exists primes. So there is a choice in V1, a choice in V2, a choice in Vk, for which for every pair of vertex subsets, Vi, Vj, there is an edge which will represent as 2 primes p cubed, just to be a bit lazy, for which p times q divides the choice that you made, p1 producted through pk. And yeah, this if only if there is a clique. So how do we implement this? Well, very roughly, we'll implement it. We're going to guess a random value. We can do this with a cycle that just adds 1 to a counter to guess a random value. And then from that, we will then do divisibility checking over and over and over again. But notice that we were able to, for a vertex subset Vi and a vertex subset Vj, we'd like to be able to pick an edge. So we'd like some non-determinism to be able to select an edge. So here's how we implement non-determinism. So suppose you have this program, like you'd like to add some random number, not random number, some non-deterministically chosen value 1, 2, or 3. Well, we are allowed to do this in a counter machine. We could just have branching. And so when I say the word guess, imagine you have a branch like this. It's just sugar for this drawing. And so instead of adding 1, 2, or 3, we'll be guessing an edge, for which we then do divisibility checking over. And so part 1 is to guess a candidate clique. And so we're just going to guess values P1, P2, P3, etc., all the way down to Pk. And we're going to multiply some value x that starts with 1, then we'll have some P1, then we'll have some P1 times P2, etc., etc. And remember, we've got implementations for these that are now hidden on the slide. So we have this guess, which is branching over all of the vertices in V1. And then we have the multiply statement, which was from the previous, which had the 2 cycles with 2 0 tests in between to enforce that multiplication is done faithfully. And at the end, the post condition is that indeed we'll have a product of k primes on the first component, and the second component will have value 0, because after every multiply step, y will be set to 0. And so this will be invariant. And then part 2, like, how do we actually check this? Well, for every vertex pair of vertex subsets, V1, V2, V1, V3, etc., we'd like to be able to pick an edge that indeed we can do divisibility checks for. We do this by indeed dividing through and then remultiplying out. If you could complete line 2, then you know you were divisible, and we'd like to restore the original value so we can do later checks. And so we do this over and over and over again. And in particular, we do it for every pair Vi, Vj. I didn't bother writing down the number of lines of this program precisely because this requires like k choose 2, and it gets really nasty really quickly, but it's less than or equal to 3 times k squared, right? The reason I'm writing this down is because I want to make sure that my program is not absolutely massive, because we want to problem time reduction. And so we have 2k many lines here. Each of these gadgets is particularly small. We have a square many steps here. And again, these gadgets were small. This guess is over a branch of maybe one of k primes, and number of nodes, n many primes, and these branches are over one for each edge. And so each of these branching statements is also small. So the whole program is polynomial in size. And the pre and post conditions here are not so important. It's just if we can get to the end of the program, then we indeed must have satisfied the statement at the top. And so we know there must be a k-clique in the original graph. And so, yeah, we can terminate in this two-counter program if and only if there is a k-clique. And the termination just says, I get to the end and I'm happy. Like I can reach the final step of the program. So I can take the loops in the program. I can choose them non-deterministically to make sure that I get to the end of the program. So I now will show how VASS can simulate, or rather I will kind of black box it. I'll show what we need to know. So we have a bound on the maximum counter. So if I go back to this program, the bound on this is at most, because the counters don't change in size here, because we're only going to divide them down and then re-multiply them up. So the maximum counter value is obtained at the end of the first part. And this is at most the product of k primes. And so then this bound going back is something like a maximum prime, right? And remember we had one prime per node, so n many primes. And by prime number theorem, that's something like n log n. So the maximum counter value you'll ever see here is n log n to the power of k. So that's n to the k log n to the k. So being really lazy, this should less than to n to the power of 2k. And I did actually compute how big the program was. It turns out to be bounded above by something like n to the 11. It doesn't actually matter what that 11 is. It's just a constant polynomial factor. And so the program's not particularly big. And here's the black box. So in polynomial time, one can construct a log of the exponent of the bound counter VASS that can simulate this bounded constant counter machine of size poly n. So if I kind of exactly plug in the values that we have set k to be 2 to the d, because we're reducing from the like 2D clique detection problem. And we have a counter machine whose bound is n to the 2 to the d. So then when we substitute this in, we have a log of 2 to the d VASS. That is a d VASS. And it is bounded by, yeah, and the bound n2 to the d is fine. So I hope this makes sense. We're just substituting in k equals 2 to the d into Rosionian statement. We yield a VASS that has like poly n many states, so it's really big, and it has log of 2 to the d, which is d many counters, and we're using this for detecting 2D cliques. Does that make sense? The remark at the bottom basically just says that I've used the word termination because I thought it was slightly friendlier. All this program needs to do is just terminate, like get to the end. And because the counters are non-negative, this is a coverability objective. I'm just at least 0 on all the components. So when I say termination, I'm being a little bit hand-wavy, but it's just the same thing as coverability. I like the phrasing. And so really, we can just ask an instance of coverability in this, twice abstracted VASS, and that will equate to asking for detection of a 2 to the d clique in a graph of n nodes. Does that make sense? Okay. So this is the whole statement, or the whole proof idea sketched out as I just explained. And we use these two parts. The first is perhaps using a known encoding in novel in this problem, and the second is just black boxing. We originally did black boxing. We used recent results from Chavinsky and Olakowski to simulate zero tests using additional counters. We had to then invoke some of the techniques of Lipton to build some gadgets to help us do some crazy things. But actually, it turns out that these machines have been known for a very long time, and so they're like lovely simulation lemmas that just do this for us. And yeah, from this we yield the theorem that, really coverability in VASS requires double exponential time under the exponential time hypothesis. And so yeah, I can conclude now with the main results. That is, the coverability in VASS can always be witnessed by doubly exponentially long runs, where that double exponential has shaved off the log d factor, answering the question of Mayer and Mayer. And indeed, we get two algorithms from this. The first is an optimal exponential space algorithm. Optimality comes from Lipton's lower bound, and a conditionally optimal time algorithm, that's double exponential time algorithm for coverability. And we claim that this is conditionally optimal under the exponential time hypothesis. And so, yeah, thank you very much. I hope you enjoyed.